All right, so today's video is going to be on derivatives and differentiability. Talked about this a little bit, so this was a little bit of review with just a little bit of new stuff being tagged on towards the end. So a couple of things that I was going to remind you of is we have these two functions right here. We have the definition of the derivative on top. We have the alternate form. We also can call that the difference quotient, and that's what's going on over there. Okay. Graphically speaking, the derivative of a function at a point P is the slope of the tangent line to P. So that's kind of what this graph is showing right here, is that here's this graph right here. I'll color that in red. And then this right here is the tangent line at this certain point of that graph. Okay. So just understanding what's going on analytically and graphically. And let's go ahead and use this information and go ahead and tackle our first example. So it says to use the alternate form of the derivative to find the derivative at x equals c if it does exist. Okay, so two examples, one here, one there, just so you are aware. So let's go for it. So for the alternate form, we're going to do the limit as x approaches 9 of f of x, which is root x, minus, plug in that, you're going to get root 9, which is 3, all over x minus 9. So we did an example like this in a previous video. You can check it out in the archives, which deals with solving these types of problems. So you can't plug in a 9. So you're going to have to multiply by the reciprocal. Not reciprocal. Conjugate. So we're going to multiply by the conjugate on both sides. And this is going to give me the limits as we approach 9 of x minus 9 on top, x minus 9, and then the conjugate. This problem works out super nice where these x minus 9s are just going to go away. And then I'm free and ready to plug in that 9 here. So 1 over root x plus 3. So when I plug in that 9, I'm going to get 1 over root 9, which is 3. 1 over 3 plus 3 is 1 over 6. All right, so this is pretty straightforward on this one. Not a big deal. Now, what we have going on for this one is we have a piecewise function, which means that I'm going to need to find the derivative on each side. And that's going to kind of be where we come down here, these one-sided derivatives. All right, in order for the derivative to exist at a point, the derivative has to be the same just to the left of it and just to the right of it. Kind of like continuous. For continuous, we said that the point to the right and the left of a function have to be the same. And what I mean by that is like just very tiny, like 0.01 to the right, 0.01 to the left, have to be approaching the same number. Same idea here for derivatives. So that's what this box right here talks about. And we're going to go ahead and tackle it. Okay, so I need to do one-sided limits at 1. So I'm going to do the limit. X approaches 1. I'm going to go from the left, which is going to give me the top one right there. Okay, and I'm using the alternate form here. So I'm going to plug in I'm going to use this x squared plus 2 minus, plug in a 1 in the top. What do I get? 3. I hope it's 3. I'm just double checking that I did some stuff. Okay. All right, minus 3 all over x minus 1. Just trying to make sure I didn't miss any talking points. So now when I do this, nice things are going to happen here because 2 minus 3 is going to be a negative 1. So if I can just purple this up, I'm going to get x squared minus 1, which factors super nicely. So when I factor that, I'm going to get the limit as x approaches 1 from the left of x plus 1, x minus 1, all over x minus 1. So what's going to happen here is these x minus 1s, whoop, I'm going to cancel out, left with just an x plus 1, and I'm ready to plug the 1 into that x plus 1. Yeah, not showing all the work in the world here, but if you're listening, you should be good to go. So plug in a 1 now, and we're going to get an answer of 2. That's the one side. I got to check the other side. And then you only, again, do this on piecewise functions. I did not need to do that on this first example over here because, first off, I knew it was continuous and it was smooth, which I'll kind of get into that verbiage in a little bit here. So let's go ahead and do x approaching 1 from the right-hand side. So we need this guy right here. So I'm going to do 3x minus, well, plug in a 1, you're going to get a 3 all over x minus 1. Again, this one's pretty straightforward. This one's going to factor for me super nice. And you're left with 3x minus 1 all over x minus 1. Going to cancel out right here. And you're left with a 3. Now, if you notice, the right and the left do not match. So it's kind of weird. Like the slopes are a little different. They kind of look like this. I don't know, I think like this. So that's not a nice little smooth point. That's actually going to be a cusp. So, or corner, whatever you want to call it. So this is not going to exist. So the derivative at 1 for this piecewise function does not exist. This right here, I'm not too worried about it. It's just saying that, hey, if these are all the slopes and whatever, or not. So I'm going to tackle this other page because it's really going to focus on what we just did with that problem. Okay. Differentiability. A function is has a derivative at a point if the slopes of the secant line from the left and from the right sides, we just talked about that, approach the same limit, except for when it's going to infinity. And then it'll produce a vertical tangent. And here are examples of 3 situations. So again, continuity, 3 things we need to do. IVT, 3 things you need to do. Differentiability, there are 3 things that can happen, okay, where it's not differentiable. So first one's going to be a corner or a cusp. So it's kind of hard to see these pictures. So real quickly, that's a corner. So if I need to find the derivative at this blue point right here, you can't. Or a cusp is if you have 2 curves or even 1 straight line and 1 curve, those are cusps. Cannot find the derivative of those points. Okay. If it's not continuous, that's pretty straightforward. So if I have a function that is like this, you can't find the derivative at this point right here because it's not continuous. And last but not least is a vertical tangent. So this one's a little bit tougher to see. But at this point right here, because a vertical tangent, I mean that tangent is perpendicular to the x-axis, then it's not differentiable. Okay. And it's kind of stated that the derivative is either going to be positive infinity, negative infinity. Just does not exist. So now let's look at this lovely picture. I think you can see it nice and clear. I'll zoom in a little bit right here. Next, we're going to state the domain of the graphs. We're going to state the domain where they are differentiable, continuous, but not differentiable, neither continuous nor differentiable. Whew. So a couple things are good here. So just differentiable. Where is this not differentiable? It's not differentiable at -2 because it's one-sided. So it's kind of like a corner right there. It's not differentiable at -1. Here it's not continuous, so it's not differentiable. And then right here we're not continuous, so we're not differentiable. So going to be differentiable from -2 to -1, from 1 to 0, from 0 to 2, and from 2 to 3. And I'm not including, if you notice, I'm not including -2, not including -1. What happened here? This should be negative. Not including -1, not including 0, not including 2, and not including 3. Okay. Now let's talk where it is continuous, but not differentiable. So this isn't going to be so much of an interval. It's actually, we're just going to find the points where it's continuous, but not differentiable. So, well, continuous, continuous, continuous. Oh, right there. So that's where it's continuous and not differentiable. Sorry. It's not continuous, so I don't care. It doesn't. Sorry. I'm not thinking straight today. Not continuous here, so I'm not going to include that. And it's not continuous there, so I'm not going to include that. So it's continuous here, here, and then there. So which one of those is going to give me something that's not differentiable? It's right here at -1. So that's the only spot where it is continuous and not differentiable. And then the last one was going to be here, not continuous, not differentiable. So we look at this one, it's not continuous, not differentiable. So pretty much going off the same thing that we just did, but now where it's not continuous, not differentiable. So it's not continuous here or here. Because if it's not continuous, it's not differentiable. So it's going to be x equals 0 and x equals 2. All right, so that just talks about differentiability. And that's going to wrap up our video.